Modern logistics centers operate at a relentless high-speed tempo, continuously processing vast volumes of commercial freight every single hour. But viewing these massive structures as single, uniform environments is a critical operational error. They are composite, multimodal systems functioning beneath a shared roof. A typical distribution center is partitioned into distinct sectors: ambient storage, regulated cold chains, and automated sortation hubs. A monolithic maintenance strategy creates an immediate resource mismatch. High-traffic docking nodes face chronic underservicing, while low-activity ambient zones are overcleaned. Achieving true environmental control requires a specialized methodology, a precise zone matrix. This approach maps every specific sector against three unyielding operational factors: traffic density, precise thermodynamic constraints, and strict mechanical automation tolerances. Building this matrix requires tracking physical contamination vectors from the loading dock, adjusting for multi-temperature chemistry, and calculating the actual economic cost of operational complexity. In these complex environments, actively controlling the facility is a highly technical subset of preventative maintenance and rigorous risk management. The logistical lifecycle inside the facility begins at the receiving dock, an area characterized by constant high-energy throughput. Because of the sheer volume of inbound freight, this specific zone acts as the primary ingress point for macrocontaminants. This comparison illustrates the root source of physical debris. On the left is a pristine AS3774 standard pallet. On the right, a degraded, non-compliant unit acts as an active contaminant generator, shedding splinters and wood dust with every movement. A busy receiving dock processing these degraded units generates several kilograms of raw timber debris every single day. This dense accumulation of splinters and loose nails creates immediate, severe puncture risks for forklift tires, threatening to halt inbound mechanical operations. Inbound processing also generates a secondary vector. Discarded shrink wrap litters the concrete, creating critical slip hazards the moment the surface becomes wet. Mitigating these threats requires a strict operational cadence. Facilities must mandate twice-daily sweeping schedules, isolated entirely to pallet staging areas. To manage the plastic waste, dedicated floor-level collection stations must be deployed. This captures the shrink wrap at the source, isolating the hazard while preserving recyclable materials. Neutralizing these macrocontaminants exactly at their point of entry ensures that dock-level bottlenecks never cascade deeper into the supply chain. Once contaminants bypass the dock, maintaining the interior becomes a strict exercise in regulatory adherence. This zone guide matrix maps operational sectors directly to their corresponding legal obligations. The columns define the required frequency, physical method, and specific equipment for each location. Looking at the storage aisles row, routine machine scrubbing serves a specific legal function, satisfying strict workplace health and safety clear aisle regulations. Similarly, utility areas like the washdown bay dictate immediate pressure washing protocols to guarantee runoff complies entirely with EPA trade waste directives. Every combination of methodology and industrial equipment must mathematically align with these legislative codes to pass safety audits. The required intervals in the frequency column are then determined by measuring the specific daily traffic density of each zone. Relying on a customized matrix removes operational guesswork, directly linking daily servicing tasks to rigid legal standards and preventing WHS liabilities. Compliance protocols shift dramatically when operations enter the highly regulated, environmentally hostile cold chain. The primary constraint is chemical. Standard ambient degreasers lose their efficacy and chemically fail when temperatures drop to between 2 and 8 degrees Celsius. Operating in chilled sectors demands specialized cold-rated sanitizing agents engineered to maintain their properties in near-freezing conditions. This introduces the frozen zone paradox. Using standard aqueous cleaning methods in sub-zero environments leaves moisture that instantly flashes into a dense layer of ice, creating a surface hazard vastly more dangerous than the original debris. Standard wet methods must be entirely abandoned in these zones. Teams pivot exclusively to minimal moisture protocols, relying heavily on dry sweeping and HEPA vacuuming. When liquid spot treatments are unavoidable, teams must deploy rapid evaporating solvents to ensure the fluid dissipates before freezing occurs. Crucially, any deeper wet treatments must be timed precisely to coincide with the facility's automated thermal defrost cycles, when temperatures naturally rise enough to permit fluid application. Effective control in the cold chain requires precisely matching chemical properties and procedural timing to the facility's rigid thermodynamic thresholds. Moving into the complex material handling zones, we encounter the rapid, continuous flow of modern automated sortation systems. Automated storage and retrieval systems, along with robotic picking stations, rely entirely on absolute optical clarity and track integrity to function. This animation shows a critical vulnerability. Mounted on the conveyor guide rail is an optical photocell sensor. Microscopic accumulations of particulate dust covering this lens directly degrade sortation accuracy, breaking the laser line and triggering systemic scanning reliability failures. The financial stakes are immediate. Failing to maintain these microscopic cleanliness standards around the hardware can directly void the original equipment manufacturer warranties. This creates a logistical paradox. Technical teams must conduct detailed particulate removal on running systems without ever halting the facility's continuous throughput. The operational solution relies on real-time radio coordination, allowing teams to access the physical equipment exclusively during pre-planned mechanical downtime. Every action taken around this hardware must then be documented directly into the facility's engineering and maintenance logs to prove compliance during service provider audits. Inside automated zones, micro-level environmental control operates indistinguishably from mechanical engineering and uptime preservation. Zooming out to the macro scale of logistics real estate, these exact operational protocols directly govern facility budgeting and economics. Many operators fall victim to the square meter fallacy, the dangerous assumption that maintenance costs and resource allocation scale linearly with a building's physical footprint. These dashboards compare two differently equipped facilities of the exact same size, a 5,000 square meter ambient warehouse and a 5,000 square meter multi-temperature automated center. The ambient warehouse maintains a low, flat resource curve. Conversely, the multi-temperature automated center requires an exponentially higher baseline resource allocation, landing at approximately $2,530 per month. This specific allocation reflects the cost of maintaining mechanical uptime and managing the specialized risks associated with cold chain and automated hardware. Proactive, complexity-based servicing is the only guaranteed method to satisfy strict equipment warranties and neutralize workplace safety liabilities. Executing these precise protocols secures the mechanical infrastructure, ensuring uninterrupted throughput across all active operational windows. Operators must audit their own facility's operational complexity against current baseline maintenance protocols to identify active physical vulnerabilities. In modern logistics, precision environmental control functions as a layer of technical support, maintaining the physical conditions necessary for continuous, high-volume throughput.